Hi folks, and welcome back to Physics with Captain Rod. I'm making this video here to help you understand how to derive a position function for an object or particle undergoing constant acceleration. So we're going to take a look at this example right here. This car, which at t equals 0 is moving at 3 meters per second and accelerating at 2 meters per second, right? And again, what is our ultimate goal here? We want to be able to derive a function that tells us position as represented by x here as a function of time. So basically, where is it going to be for all time under these circumstances? Now, the first thing you typically do is you define a set of coordinates here. And I'm going to do this in green. And actually, if you give me a moment here, humor me. Take a little bit longer than I probably need to, but so I'm going to draw myself a coordinate system. And this is what we would use to, I guess, keep track of the particle, if you will. Now, you can put a coordinate system in a problem anywhere you darn well want. Now, if I were to put the coordinate system, say, right here, the initial x-coordinate of the car would be 0. The initial y-coordinate is some positive value. Now, with the coordinate system oriented like this, the y-coordinate of the car is not changing. So we might as well just orient it so that the y-coordinate is 0 as measured to, we'll say, that dot on the car. Now furthermore, if we put our coordinate system over here at t equals 0, the car has some positive value for x, and there's nothing wrong with that. We could also put the coordinate system over here at t equals 0. That car would have would be at some negative x coordinate, but I like to say simplicity is king. We might as well just put the coordinate system and orient it in such a way that at t equals 0, the x-coordinate of the car is 0. So I'm going to choose that location for the coordinate system in this problem. Now, I always recommend in most problems, start with your velocity information here. So let's start with that. At t equals 0, the velocity of the car is 3 meters per second. So I'm going to go 1, 2, 3, put a dot here. And again, in units of meter per second. Now, a second later, our car is accelerating at 2 meters per second. So a second later, our new velocity is going to be 5 meters per second. And then a second later, 7 meters per second. And this is going to map out a line. Now I'm just going to run that out here to some time t here. This distance on this picture, whoops, let me make it straight, is the velocity that goes with this time. Now, the purpose of this video was really how to derive a position function from a velocity function. So I'm going to go ahead and shorthand this part. This function here is linear. So that means it mathematically looks like this, mt plus b, where m is some sort of slope and b is the y-intercept. The slope of a velocity graph is your acceleration. And the b is the intercept. So our velocity function here, the equation that describes it, is 2t plus b. Now, this method that I use, calling this a linear function and using the acceleration for the slope and reading the intercept off the graph, will work for any problem where the acceleration is constant. Right, moving on to the next graph here. So as time goes on, you'll notice the delta x is getting bigger and bigger and bigger, and I try to put a motion diagram in here that shows that. So this graph, that means it's going to have some concavity to it. And so this distance on the graph, whoops, I meant to do that in red. Third time's a charm. Is the x that goes with whatever time this is. Now, getting from here to here, the important concept here is that the delta x, the change in position of the car, is given by this area right here. The area under that velocity graph tells us the change in position. And this is a trapezoid, this geometry right here. And when you find the area of the trapezoid, I like to say it's left plus right divided by 2 times the width. So in this example, that's going to be 3, and I'm going to leave the units off. I'll put NCU for note consistent units. Right? Plus the right-hand side, and here's the trick here, is that the right-hand side is described by this function. 2t plus 3 divided by 2, and then the width of our trapezoid is what we're calling t. So our change in x is going to equal, I'm going to clean this up a little bit. Now notice 3 plus 3 is 6, divided by 2 is 3 times t, so 3t plus 2t squared over 2, so I'll just put plus t squared. Now, delta x is final minus initial. Our initial x coordinate is 0, so this is effectively x final minus 0. So our function here can be just simply expressed 3t plus t squared. So here's how to use our velocity graph and the area to derive a function for position of the car. I can put in any value for time I want. It's going to tell me the correct x coordinate. Again, this is only good while this acceleration remains constant at 2 meters per second per second. Now, for those of you who are in my calc-based physics, and you might be wondering why is Mr. Price asking me to watch this video here? This can all be done by integrals and derivatives and whatnot. Well, fundamentally, it's the area under this curve that gives this relationship, tells you your position. And I always start all of my classes, regardless of the math level, by using area to do these calculations. In fact, usually we start by numerical examples. Instead of t here, we put maybe 3 seconds or 5 seconds. Then we upgrade, if you will, to more generic examples where we're using this same method, though, same approach to find functions. And I'll save the more mathematical methods for other videos here. Right? So anyway, again, the purpose of this video, how to use a velocity graph here and area under the curve to write a position function for a particle undergoing a constant acceleration. I hope that this has helped you learn how to do that. Have a great day.